Okay, good morning. Today we're going to talk about some more probability. It's kind of these two lectures are a bit of a crash course in probability, so I'm going to overload you a little bit with probability stuff, and then in the next lecture we'll see some more applications to algorithms. Okay, so last time we talked about probability and probability trees and outcomes and events and computed the probability of some events. And this lecture is going to be a lot about random variables. And as it turns out, random variables are really like the real thing you mostly study in probability. I mean, events are all good and so forth, but in the end, it's mostly about studying random variables. So what is a random variable? Actually, this is the case where it's very nice, I think, again, to take this perspective on probability in terms of like randomized computer programming that we do take. Because then a random variable is just like a variable in some randomized code. Let me add a few things to this definition. One thing is it should be a random variable whose type is real number. So random variables represent real numbers. And to be a little bit more accurate, it's more like it's the variable's value at the end of the execution. That's really what a random variable is. Okay, it's the value of some variable at the end of the execution of some randomized code. So this is one definition and one way you can think about it. So for example, here's a little bit of randomized code modeling a common situation. Let's say you roll two normal six-sided dice and you let S be their sum. And then you also check to see if that sum is 12. And if it is 12, then you set I to be 1, and otherwise you set I to be 0. So at the end of this code, there's two variables, S and I, and these are random variables. I can be either 0 or 1, and S can be any number between 2 and 12. Okay, so when you see a randomized code like this, it's a good idea, at least when you're just beginning, to draw these probability trees. In this case, it's a little bit too wide to fit on the slide, so I kind of sketched it. So the first thing that happens is you do this rand int 6, roll the first die, and has 6 possible return values. You have a branch for each, and on each you do the same thing. You do this other rand int. And it also has 6 possible branches. So really there's 36 leaves or outcomes at the bottom here, but I couldn't quite draw them all. And before I told you should label all the leaves with which are outcomes by the sequence of return values you got from the random number generators. And in this scenario, since we're going to be talking about random variables, it's also good to label them with the value of the variables at the end. So this very first outcome where you roll 1 and 1, that's the outcome. S is 2, and this I is 0. Or this arbitrary one I put in the middle where you roll 4 and 3, the outcome is 4, 3, S is 7, I is 0. And the last one, 6, 6, S is 12, and I is 1. Okay, so you see, one thing you can see from this tree is for each of the variables in question, S and I, their value depends on what the final outcome is. Their value at the end of the code. So actually, because of this, you can think of random variables in another way. This is sometimes a bit more like the official definition of random variables. So a random variable, let's call it X, is just any way of like assigning a real number to an outcome. I mean, for a random variable X, its value is some real number that depends on what the outcome was. Okay, and so you can think of it as just an assignment of a real number to each outcome. And in fact, therefore, it's a function. Okay, from the set of all outcomes, which we call the sample space. Remember, the set of all outcomes or the set of all leaves is officially called the sample space, and we wrote omega for it. But in any case, it's a function that maps each outcome to a real number. Yep?
Is it still random even if it maps each outcome to the same number?
Yeah. So it is true that you could have a variable that always has the same value no matter how you execute the code, and you may still call that a random variable, even if it happens to be like the constant function, or if it always has the same value. In particular, it's not true that a random variable has a different value for each possible outcome. There can be more than one outcome that leads to a random variable having the same value. For example, there's more than one way to roll or to get 7. You can see there's several ways to get I equals 0. Okay, so if you think of it, sometimes we'll think of it like with this interpretation where it's a function. And then, for example, if you take this random variable s, which is the sum of the two dice, here, for example, 1, 2 is an outcome, and s maps 1, 2 to 3. When the outcome is 1, 2, the sum of the dice is 3, and so forth. Okay, so it's important to keep both of these perspectives in mind. Okay, so we're going to be talking about random variables throughout most of this class, and also you'll be, working with them on the homework, which is going to be out just after this lecture. And you very often need to introduce some random variables into the story. And there are many ways you can do that, so I'm going to actually kind of illustrate them over the next few slides. So one way you sometimes introduce them is kind of retroactively. So for example, I told you this little experiment, and I showed you the code where you rolled 2 dice, and you let s be the sum and I be 1 if and only if you got 12. But then if you were talking about the situation, you might just add this sentence, like let d be the random variable given by subtracting the first roll from the second roll. So this d wasn't actually in the code already, but this sentence just kind of tells the other person, the reader, that they should imagine that you set d to be the second roll minus the first. Okay, so we can think of this as if it had been in the code, or we can think of it as a function that tells you for each outcome what d's value is. So if the outcome is 1, 1, the difference, I guess that's why I called it d, is 0. If the outcome was 5 and then 3, then the difference would be minus 2, and so forth. Another way you can introduce a random variable is in terms of other random variables. So at this point, if we have s and I and now also d, you can also just say let y be s squared plus d. There's no particular reason to look at this weird quantity, but let's say you did. Again, it's kind of like you could imagine that somebody wrote this as the last line in the code, compute s squared, compute d, and let y be s squared plus d. But you can also just say this. Okay, and then for example, this random variable y, when the 2 dice are 5 and then 3, I guess would be 8 squared, which is 64, plus negative 2, which is 62. Some strange thing. So here's another example. Let's keep up with this roll of 2 dice. And suppose you say, okay, suppose you win $30 if you get double sixes, and you lose $1 otherwise. And you may say, let w be the random variable which represents your winnings in dollars. How could you express w in terms of random variables we already talked about? Like by a formula. I mean, you can just say this, but you can also represent it sort of by a formula in terms of other random variables. Yeah?
W equals 30 if x and y are both 6 and 1 otherwise.
You mean this y?
No, $1 otherwise. Well, x and y is the variable where x represents the first row and y represents the second.
Yeah, actually we didn't, in this story so far, we didn't even actually give names to the 2 dice rolls. Maybe we could have assigned them names. Those would also be random variables, but we didn't. Yeah, this is fine. I mean, it's kind of similar to this description as well, but yeah.
You can add 31 times I minus 1.
Yeah.
Total each time, to W each time?
Yeah, maybe just once. I mean, this is what I had in mind. I mean, I don't know if you remember all these, it's early, these random variables I mentioned, but we have this random variable I, which is 1 if you get double sixes and 0 otherwise. So you could say, if you want, that W is 31 times I minus 1. Because if I is 1, this would be 30, and if I is 0, this would be minus 1. I mean, you don't have to do this. This is also a perfectly fine way to describe what W is, but if you want to compute something about W, maybe having an arithmetical formula might help. Any question? Okay. Another way you can introduce a random variable is actually just without even bothering to talk about any randomized code or any experiment. So for example, you'll start to see things like this. Let x be a Bernoulli 1/3 random variable. I hope you remember this Bernoulli 1/3 is something that sort of outputs 1 with probability 1/3 and outputs 0 with probability, well, the rest, 2/3. And you can just say this. I mean, really, it's kind of like you're telling the other person to imagine that there is like one line of code that says x equals Bernoulli 1/3. But at some point, you can even stop dispensing with the code. Or here's a trickier one, which I guess cannot really be done with one line of code, but it is something that you're allowed to say. Let t be a random variable which is uniformly distributed on this set, 0, 2, 4, 6, 8. You'll start to hear this phrase a lot in probability, uniformly distributed. This just means each of the possibilities has the same probability. So in this case, since there's 5 numbers in the set, it means that t is supposed to be 0 with probability of fifth, 2 with probability of fifth, 4 with probability of fifth, etc. So this is something you're just allowed to say. And again, it's like you're sort of telling the reader or the other person to imagine like some code that generated t with these probabilities. Could somebody suggest such code that would do that? Yeah?
2 times radian 5 minus 2.
I think so, yeah. 2 times, well, it's the same as this, yeah. The response is 2 times randin 5 minus 2, or this. Yeah, so you want to, you need to get 5 different things with probability 1/5 each. So randin 5 is a good way to do that. But then you have 1, 2, 3, 4, 5. But if you then double it and subtract 1, you'll indeed get t taking each of these numbers with probability 1/5. Okay. So, as I said, we're going to talk a lot about random variables today. But in the previous class, we mostly talked about events. So we need some kind of connection between random variables and events. So let me talk about such connections now. Well, if you have a random variable, you can often use it to describe an event. So one thing you might do, again, keep your head fixed on this example where you roll 2 dice and s was their sum. You could say, now let A be the event that s is at least 10, that you rolled at least 10. Okay, so remember an event is a subset of the outcomes. So what are the outcomes corresponding to this event? Yeah, sure.
5, 5, 5, 6, 6, 5, 6, 6.
Yeah, there's a couple more involving 4.
Oh, right. 4, 6, 6, 4.
Yeah, that's right. Yeah, it's all the ways that you can get at least 10. Thank you. So here they are. Okay, and so the probability of this event, well, the probability of this event is, well, there's 6 outcomes, and they each have probability 1/36, because, your probability tree just has 36 paths. So the probability of this event is 1/6. And by the way, this is shorthand. Normally here in probability in these square brackets, you're supposed to write an event on the inside, but this is like a shorthand for this event. The event of all outcomes L, such that, remember, this is s's value on outcome L. If you're thinking about it in this function way, where kind of s gives to each outcome a value, the sum of the 2 dice, the event that it's at least 10. Okay, so this is some shorthand notation where you kind of quickly create this little event here, s greater than or equal to 10, and then evaluate its probability. Okay, so that's one common thing you'll see. You'll have some random variables, and you'll make up some events based on them because you're interested in their probabilities. You can also go the other direction and take an event you might have and build a random variable based upon it. And here, there's really one key way you almost always do this. Okay, there's one very common critical way to take an event and build a random variable based on it. And it's called making an indicator random variable. And it's pretty natural, actually, if you think about programming. Like, you check if the event occurs, and then you set a variable to 1 if it occurs, and 0 if it didn't occur. It's kind of like true or false. It's very convenient for it to be 1 and 0. So this is a definition. If you have any randomized code and A is an event, it's often a good idea to introduce this indicator random variable. Let's say we'll call it x. And you just specify that it's 1 if the event occurs and 0 if it doesn't occur. Okay, so you can just introduce x like this, or you could imagine like sticking a line of code at the end that checked if A occurred and set x appropriately. Okay, if you want to think of it as a function that maps all the outcomes to a real number, then x's value on a given outcome L, or a leaf in the probability tree, is just what we said. It's 1 if it's in the event, because an event is a subset of outcomes, and 0 if it's not in the event. Okay, so we'll have some more to say about indicator random variables later, but I need to give you a little bit more probability theory at this point. By the way, for example, if you remember this code from the beginning, where we just had 2 random variables, s, the sum of the 2 dice, and I, which is 1 if you got double 6s and 0 otherwise, this I was an indicator random variable. It was the indicator of the event that you got double 6s. You know the gambling term for double 6s? It's not quite as well known as the double 1s one. Oh, I know you know it. Come on. Well? All right, you can Google it, I guess. Okay. So we had a notion that events were about events being independent. And now there's also a notion of random variables being independent, which is equally important. So here's the definition. And then really, it's in terms of the definition of events being independent. So random variables x and y are said to be independent if all of these events of the form x equals u and y equals v are independent. So for every u and v, you get an event x equals u and y equals v. And if they're all independent, then you say x and y are independent. And there's a similar definition for you have 3 random variables when they're independent. If all the x equals u and y equals v and z equals w are independent events. And the other important thing to remember is or for me to tell you, is that this principle of independence that I mentioned last time still holds. This is like saying, suppose you have some code, and x's value is just determined by these lines in the code, and y's value is just determined by these other lines in the code, and you can prove that the lines of code, this block of code cannot affect this block of code and vice versa, then you may deduce that x and y are independent random variables. Okay, any questions about that? All right. So, okay, that's it for random variables to start. And now we're going to talk about the most common thing you're ever interested in when it comes to random variables, which is the expectation of the random variable. Okay, now expectation is a funny term because there's 3 equally used synonyms, which is a little bit annoying. It's also called the expected value of the random variable. It's also called the mean of the random variable. All of these things mean exactly the same thing, and I guess you just say one and not the other if you're bored of saying the other one. And intuitively, what is the expected value or the expectation of a random variable? It's kind of like if you have some code and it ends by generating some variable. Imagine you ran the code millions and millions of times, and you took the overall average, just the normal average of what that variable's value was over the millions and millions of times you ran the code. That's intuitively what the expected value is supposed to represent, or the mean. Okay, so that's the idea behind it, and then the actual definition is given by a formula. So let's say you have a random variable x, and the sample space, the set of all outcomes, is omega. So you can think of x as a mapping from all the outcomes to real numbers. And what do you do? I hope you find this somewhat natural. You go over all the outcomes, and you take the probability of that outcome times the value x has for that outcome. Okay, so for example, imagine you had 10 outcomes, and they all had probability 1/10. So these were all 1/10. Then it would just be the sum of all of x's 10 different values over 10. In general, it's you count x's value with probability proportional to the probability it takes that outcome. Okay, makes sense? Okay, so let's do some examples. So here's a simple example. Let R be the roll of a standard 6-sided die. Okay, so each 1 through 6 comes up with probability 1/6 each. So how do we compute its expectation? Well, I mean, if you look at the formula, you go through all the 6 outcomes, and you sum up. Each one has probability 1/6, and then the values of the outcomes are 1, 2, 3, 4, 5, 6. So if you do some quick arithmetic, you'll find that this is 3.5. Okay, so the expected value of a roll of standard die is 3.5. Now, by the way, what is the probability that R equals 3.5? Yeah, it's 0. So this is just to say that despite the fact that it's called expected value, you don't necessarily, expect it to have that value. Well, this is I probably call a concept you're used to, that the mean of a bunch of numbers doesn't have to actually be one of the numbers that could be taken on. Okay, let's do another example. Let's go back to this scenario where you rolled 2 dice, and we said you win $30 on a roll of double 6s, and you lose $1 otherwise, and let W be the random variable, which is your winnings. What is the expected value of this? It's kind of like how much in one roll do you expect to win, or if you played this game 1,000,000 times, what would the average amount you win be? Okay, so again, there's 36 outcomes here. Always probability 1/36, and most of the outcomes give you a value of -1, and there's one outcome where you get a value of +30. So if, again, you do some arithmetic, this is -5/36, which is like -13.9 cents. Okay, so, I mean, you probably would have guessed this is not the best gambling game for you, and on average, you lose 14 cents if you play this game. Okay, so now this calculation got a little bit annoying. Let me show you another annoying calculation, and then we'll try to learn some tricks that will help us compute expected values more easily. Because this is like the number one thing you ever kind of do in probability life. You have some random variable, you try to compute its expectation. Okay, so let's say we roll 2 standard dice, 1 through 6, and I'll give them names in this case, R1 and R2, and let S be their sum. And now I want to compute its expectation. So now it starts to get a little annoying, right? There's 36 possible outcomes, 1, 1, 1, 2, 1, 3, all the way up to 6, 6. Each has probability 1/36. The value of S when you get 1, 1 is 2. When you get 1, 2 is 3. Up to 12 when you get 1/36. So now you have to compute this number. Any guesses for what it is? Yes, 7. Who said that? Okay, yeah. Do you agree, Marcel? All right. It's right in the middle, yeah, if you roll 2 dice. Yeah, it turns out to be 7, indeed. So, okay, you can compute this arithmetic. But I'll show you another way that you can do this computation more easily. So this is, what I'm about to tell you is one of the top tricks in all of probability theory. It's a very, very simple trick. And it goes by this name, linearity of expectation. So it's a very simple trick, but it's great. You should strive to use it whenever you can. So what is linearity of expectation? It's this. Let's say you have an experiment, some random code, and it produces 2 random variables, x and y. And you're interested in the expected value of x plus y. Then, I mean, life is great. It's the same as the expected value of x plus the expected value of y. Okay? Seems reasonable. Although, actually, as time goes on, you may find yourself, it sounds dumb, but you may find yourself getting amazed by the fact that this is true. And in particular, at first it doesn't seem weird, but in particular, you'll later be amazed that this is true even if x and y are not necessarily independent. So like in the dice roll, which we're about to apply this to, they are independent. But Even if they're not independent random variables, this is still true. This always holds. Okay, so I will prove this to you, and it'll fit in this slide. Okay, so we're interested, really, I mean, this is a bit of a shorthand. It's really like we're saying, let z be the random variable, which is x plus y. And we're trying to compute the expected value of z. Okay, so here's the whole proof. So let me go over it. We have the expected value of z, so let's just write down the definition of what that is. By definition, it's the sum over all the outcomes L, the probability of that outcome times z's value when you get outcome L. Okay, by definition, z is just the sum of x and y, so it's sum over L, probability of L, times the sum, x's value on outcome L plus y's value on outcome L. And now this is like a number times the sum of two numbers. So you can like open up the parentheses, and you get this number times this number plus this number times this number. So you can separate those out in your sums, and you just get the sum over L of probability of L times x of L, which is the expected value of x, plus the same thing for y, the expected value of y. Okay, so there's really nothing to do in this proof. You just keep writing down the steps as they occur to you, and you end up proving it. Any questions? Okay, so there's a couple other things that are equally true, equally simple, and also go by the name of linearity of expectation. One is this. Actually, I wrote this in few steps. If a and b are just numbers, not random variables, but just numbers, then a times x plus b is also a random variable. And its expectation is a times expected value of x plus b. For example, imagine b is 0. This is saying that if you have a random variable x, the expected value of a times x, where a is just a number like 5, is like 5 times the expectation of x. I think that's okay, right? I mean, if you have a bunch of outcomes, you multiply them all by 5, the average will also go up by a factor of 5. And similarly, if you take all the outcomes and add 3 to each of them, the average will go up by 3. And you can also take this and prove by induction that it holds for any number of random variables. If you have the expected value of the sum of n random variables, it's the sum of the expectations. So everything on this slide is called linearity of expectation, and it's a great set of facts that we will use repeatedly. Okay, so let me give you an example of its use. And it'll be in this little example that we looked at before, where you roll 2 dice, call them R1 and R2. Let S be the sum, R1 plus R2. And we wanted to know the expected value of S. Well, now we can, S is R1 plus R2. So this is, by linearity of expectation, the expectation of R1 plus the expectation of R2. And we saw earlier, this one was not so bad to compute, that if you have one die randomly thrown, giving you a value between 1 and 6, its expected value is 3.5. So it's 3.5 plus 3.5, which is 7. Okay, so it simplifies a little bit that like painful calculation with 36 outcomes we saw before. Okay. Now, let me take you back a little bit to we were talking about how to go from events to random variables, and I told you there's one main way. It's to look at indicator random variables. If you have an event A, the indicator random variable is just a random variable which is 1 if A occurs and 0 if A doesn't occur. And here's a very simple fact, but also very nice. If you have an event A and x is its indicator random variable, then the expectation of x is the probability of A. Can somebody say why that's true? Yeah? Yeah, so keep going. Yeah, I mean, it's just not too tricky. I mean, you just plug it into the definition. I mean, this is what you said. You just sum over all the outcomes, probability of the outcome times x's value on that outcome. Okay, so every outcome is either in the event A or not in the event A. When it's in the event A, by definition, the indicator random variable is 1. And when it's not in the event A, the indicator random variable is 0. So these terms go away. This 1, you can make it disappear. So you're just left with the sum of the probabilities of all the outcomes in A, which is the probability of A. Okay, good. So we've talked about expectation and indicators and linearity of expectation. And I want to tell you about the combination of these two things because these two concepts are like best friends forever. It's almost like a method. Like so many problems can be solved by like just putting these two simple ideas together. Linearity of expectation and indicator random variables. Many problems, homework problems, lots of things. So try to think about this if you're trying to compute the expectation of a tricky random variable. So let me give you an example. Here's a probability puzzle. Let's say you have 251 students in a class, and the TAs randomly permute the midterms before handing them back. So they just randomly permute the midterms and just give them out one by one. So probably you're not actually going to get your own midterm back, but you might by a fluke. Let's let x be the number of students that get their own personal midterm back. And let's try to figure out what is the expected value of x. Yes? Oh, you've already solved it. Well, hang on. Yes, it's going to be 1, but don't say it. Don't tell. Let me illustrate the method on this problem. Okay. 251 is a large number, so let's try 3 first. Actually, maybe I should have tried 2 first. Oh, let's do 3. Okay, so I mean, let's imagine this with the experiment. You got 3 students, student 1, 2, and 3. And then the midterms are like handed back to them in a random order. So I mean, it's like a random permutation of the numbers 1, 2, and 3. 1, 2, 3, 1, 3, 2. So there's 6 of them, and they all have probability 1, 6. That's sort of posited. And we can compute in each case for each of the 6 outcomes, what is the value of x? This is on the right column, x, the number of students that got their own midterm back. So here it was amazing. All 3 of them did. Here it was 1, 1, 0, 0, 1. So if we compute the expectation in this case with 3 students, it's 1 6 times 3 plus 1 6 times 1 plus dot 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 dot, which happens to equal 1, as well predicted in the 251 case. Okay, so that's fine, and this would be like a very nice, normal way to solve this problem. But you can see that if there's 251 students, you're going to have a bad time trying to fill in such a table because there's 251 factorial different outcomes, and it's pretty tricky, right? I mean, you could say, all right, let's say we have some crazy outcome. We'd have to count the number of students that got the right midterm in that case. How many outcomes are there where 11 students get their own midterm back? It's kind of complicated. But you can do it using this concept of putting together linearity of expectation and indicator random variables. So the game in this trick is, this idea is to always try to take your complicated random variable and express it as a sum of, hopefully, indicator random variables. You have to cleverly introduce some indicator random variables, show that the random variable you care about is the sum of them in some way, and then you're in good shape. So let's see how that works. Let's let A sub I be the event that the I student gets their own midterm. So I just introduced 251 events there, A1 through A251. And I'll let xi be the indicator of ai, 1 or 0, depending on whether they got their own midterm. Okay, and now how can I represent x in terms of what I have on the slide so far? It's the sum not of the AIs, but of not the expected value of AIs either. Yeah, it's the sum of the XIs. So you got to get the type checking correct. AI is an event, so that's like a set. You cannot sum these things together. An XI is a random variable. I mean, imagine you did the code, right? You like generate a random permutation, then you went through all the students, and you said, okay, let XI be 1 if the ith person got their own exam. And then you needed to know how many students got their own exam. Well, you add up all the XI variables that you had and call that X. Okay, and now we're in good shape. So we really care about the expectation of X. By linearity of expectation, it's the sum of all these expectations. And we also know that the expected value of Xi is the probability of AI. This is the fact that the expectation of an indicator is the probability of the event that's being indicated. So it's going to be enough to try to figure out what is the probability of AI. So fix some I, like 100. And you fix the 100th student and say, what's the probability that the 100th student got their own midterm back? Well, what is it going to be? What is it? 1 over, yeah, n did you say? Yeah, it's 1 over the number of students in the class. Oh yeah, n. Very good, yeah. I should have written, this is like a mistake, right? N should be 251. I don't know why I wrote n. Thank you. I got to fix this. Yeah, it's, because if you just fix on one student, right? The midterm that they get back is like a random midterm among the n, or in this case, 251 midterms. So the probability they get their own midterm is 1 over 251 for each I. So all of these numbers are 1 over 251, and there's 251 of them. So the expectation is indeed 1. Okay, so it's kind of cute. It doesn't actually depend on the number of students in the class. No matter how many there are, it's always, on average, 1 person gets their own midterm back. Okay, any questions about that example? Okay, let me now give you another formula for computing the expectation. And here it is. Let's say you have a random variable x. This is a different way to compute its expectation. It looks similar to the definition, but it's different. You sum over all values u that x may take on, u in the range of x, the probability of it taking on that value times that value. So let me make some remarks about this. So just range of x, it's just the set of real numbers that x might take on. Here, x equals u is an event, remember? This is the probability of this event. And some people take this as the definition of expectation, but we do not. We already saw the definition where you summed over all the outcomes, the probability of the outcome times x's value on that outcome. This is kind of, as we'll see in a second when we prove this, is kind of like grouping those summands together based on what x's value was. So for us, we take this as like a formula and not as the definition. So let's indeed prove this formula. It's kind of like counting by 2 ways, but if you don't appreciate that, then it's fine. I mean, this is the whole proof. So let's take a look at it. So I want to justify this formula. So I want to compute the expected value of x. And this is our definition. You sum over all the outcomes, the probability of that outcome, times x's value on that outcome. And now I'm going to break up this sum kind of into groups depending on what x's value is. So for example, if x is the sum of 2 dice, there's 36 outcomes, like 1, 1, 1, 2, 1, 3, up to 6, 6. But there's only like 11 different values x can take, 2, 3, 4, 5, 6, up to 11. We're going to kind of group together the outcomes where x gets the same value. So I can sum over all values u in the range, and then sum over all the outcomes L which lead to that value, the same thing. And now it's like a little arithmetic. If you're inside this inside sum, x of L is by definition u. So I can just plug in u here. And now inside this sum, you're summing over L, and this u is just like a number that doesn't depend on the index, so I can bring it out. And now here on the inside, we just have the sum of probability of outcome L over all outcomes which make X U. It's like the sum over all, let's say, pairs of dice rolls which lead the sum to be a particular thing like 7. And that's the definition of the probability of X equals U. Okay, and now this is the same thing as this. I just reversed the two things we're multiplying. Okay. So let's see a little example of using this formula. And this is this example has no special meaning. I just made it up kind of randomly. Let x be a uniformly random integer between 1 and 10. So I imagine just x is randint 10. And then I'm going to let y be x mod 3 for no special reason. And I'm going to ask, what is the expected value of y? Now, it's actually not so bad to compute this from the definition. There's only 10 outcomes. They all have probability of 10th. You can write it down. But just to illustrate the use of this formula, first of all, what is the range of y? Yeah, 0, 1, and 2. And so now we'll use the formula. It's the probability that y is 0 times 0 plus the probability it's 1 times 1 plus the probability it's 2 times 2. Now you can see, okay, luckily I can just drop this term, and I can drop this 1. So it's just this. So there's a bit less to calculate. And yeah, what is the probability that y equals 1? Well, it's hard to do in your head. But y equals 1 is really an event, right? It's the event that the outcome x is either 1, 4, 7, or 10. And the event that y is 2 are the outcomes 2, 5, and 8. So this one has probability 4/10. This one has probability 3/10. So by some weird miracle, it turned out to be 1. But whatever. It was just an illustration of using this formula. Okay. Just a small comment about this. Here, when we did this calculation, we didn't really need to remember how, in some sense, how y was created to compute the expectation. What we really just needed in the end was to know all the probabilities that it took, that it had for taking on different values. And this is a good thing if you have a random variable to summarize. For each value that it may take, what is the probability it takes that value? And this is encoded in something called a probability mass function. So another definition for you. If you have a random variable x, the probability mass function, you can think of it just basically as like a table where, like, for each of the values that x might take, you write the probability that it takes that value. Okay, like if x is the sum of 2 dice, it's like 2 is taken with probability 1 over 36. 3 has probability 2 over 36. 4 has probability 3 over 36. No. Yeah. And in general, a bit more formally, how can you summarize it? The probability mass function written p sub x is just like a mapping from values to probabilities. This is px of u is just the probability that x equals u. It's almost just like a shorthand for these numbers. Okay, and what are the properties of these probability mass functions? Well, these are all pretty straightforward. This function px of u, it's usually 0 because, I mean, usually a random variable only takes on finitely many different values. So almost all the values it never takes on. It's only non-zero if u is in the range of x. And of course, these are events that partition the sample space. I mean, x is always some number. So the sum of these probability mass function values is 1. And this is like just a shorter way to write our expectation formula. The expectation of random variable x is the sum over all u in the range, the probability of x being u times u. Okay, so this is just to say, if you want to figure out the expectation of a random variable, you don't necessarily have to know all the outcomes and so forth. You just have to know these probability mass function values. And because of that, since one of the main things you care about with a random variable is what's its expectation, stuff like this, it actually captures a lot of information about the random variable. Not all of it. It doesn't capture the relationship between x and other random variables, but most of the information you need to know about it. And in fact, sometimes random variables are just defined by giving a PMF, but with no reference to an experiment. So you might say, let x be a random variable where the probability of x being 1 is 0.2, the probability of it being 2 is 0.5, and the probability of being 3 is 0.3. And this is like a legitimate statement as long as these numbers are non-negative and they add up to 1. You might think a little bit about how you could write some code that generated this random variable x. It's not completely straightforward. In fact, there's some homework problem, I think, of this type. Oh, I discussed this already. Yeah, for this to be a legitimate statement, there have to be non-negative numbers adding up to 1. OK, let me give you a few more facts and formulas, and then we'll talk about some problems. So this is the formula this formula for expectation is actually the one you typically use when you're trying to compute expectations, not so much the definition. And you can generalize it in some ways. So for example, if I asked you to compute the expected value of x squared, really this is like another random variable. X squared is another random variable. You use the formula in the natural way. It's the sum over all possible values that you might take times the probability that x takes that value times u squared. You can prove this for yourself. It's not hard. It follows the same proofs we've seen before. Or for example, if for some bizarre reason you wanted to compute the expected value of the sine of x, then it's the sum over u, probability x equals u, times the sine of u. Okay, in general, if you have the expected value of the function of x, this would be the formula. And this also works even if you have more than one random variable, like x and y. The expected value of g of x and y is the sum over all possible values that x might take and all possible values that y might take. The probability that x and y take on those values simultaneously times the value you're interested in, gu of v, in that outcome or that event. So for example, this is another just like toy made-up example that's sort of pointless, but it illustrates the formula. Let's say we have this code. X is randint 2, so it's 1 or 2 with probability of half. And then y is randint x plus 1. So if x happens to be 1, then y is a random number between 1 and 2. If x happened to be 2, it's a random number between 1 and 3. So I just want to give a situation where like y depends on x, so it's like not so straightforward. And now suppose I ask you, what is the expected value of x times y? Well, here there's really nothing more you can do than this. I mean, you just got to do this. You say, well, I mean, the range of x is 1 and 2. The range of y is 1, 2, 3. So there's 6 possible ways that it can happen. X can be 1 and y is 1. X is 1 and y is 2, etc. We write down this computation, and we put in x times y over here. And then what is the probability that x is 1 and y is 1? Well, x would have to be 1. That's probability a half. And then in that case, you're doing randint 2. Y would also have to be 1. That's another probability a half. So it's a quarter. Similarly here, the probability that x equals 1 and y equals 3 is 0, etc. So then you add it all up, and it's some number, 11/4, I guess. And that's the answer. OK, so this is how you do an expectation of something involving more than one random variable. And while we're on this subject, we just computed the expected value of x times y is 2 3/4. What is the expectation of x? Yeah, 1 1/2, 3 halves. It's 1 with probability a half, 2 with probability a half. The expectation of y, I won't make you do it. It's 7/4 if you write for 1 minute. And I bring this up to observe that, notice that expected value of x times y is not expected value of x times expected value of y. So please do not think that that holds. even though expected value of x plus y is expected value of x plus expected value of y. That one is true. But it is true that if x and y are independent, that this holds. And that's another good fact to know. If you have two independent random variables, the expectation of the product is the product of the expectations. So in the previous example, they weren't independent. I mean, there's no trick. I mean, y's value really depended on x's value. But if they are, this is true, and it's good to know. Here's the proof. It's pretty short. So what is the expected value of x times y? Just by the formula, it's the sum over all u and v that x and y might take on, the probability that x equals u and y equals v, times, well, what you're interested in, the product uv. And if you remember, the definition of x and y being independent is that the product that the probability that x is u and y is v is the product of the probabilities. It was exactly that x equals u and y equals v are independent events. So then we get to this line, and now it's just some rearrangement. You put the u stuff together and the v stuff together, and I use this probability mass function notation. And this is what you would get if you just expanded out all these brackets. And this is the expected value of x by the formula, and this is the expected value of y. Okay, so it's a very short proof of this fact. Okay. I want to tell you about two more kinds of random variables, and then we'll see some problems. You might not know it, but you have two favorite kinds of random variables. I will tell you what they are just now. Okay, the first nice kind of random variable that comes up a lot is called a binomial random variable. It has a funny name, but it's a very simple concept. Basically, it's like, imagine you have a coin that comes up heads, not 50-50, but with probability p. And imagine you flip it n times, and you ask yourself, how many times did it come up heads? That number is called a binomial random variable. Okay, so if I write this, x squiggle binomial np, that means x is a random variable, which counts like the number, you should think of it as like the number of heads you got if you flipped n coins, each coming up heads with probability p. Or more symbolically, imagine as code that you wrote x as x1 plus x2 plus up to xn, where each of these xi's is Bernoulli p. Remember, that means it's 1 with probability p and 0 with probability 1 minus p. Okay, so x is like counting the number of 1s you got. Okay, so what is the range of this random variable? Yeah. Yeah, 0 through n. It can be, the number of heads you got in n flips can be any number between 0 and n. And what is the probability? I mean, these are all the basic questions you ask yourself when you have a new kind of random variable. What's the probability that the number of heads you got is some number u? This is a little bit tricky. Well, a little bit. Let's think it through. Now, the xi's, which are like the coin flips themselves, there's 2 to the n possible outcomes. Like, they can each be either 0 or 1, heads or tails or heads. And x is u when this outcome has u 1s in it and n minus 1 zeros. Right? Because it's like you're counting the number of 1s or adding up these bits. So what is the probability of an outcome? Let's say you have a specific outcome, like a specific string with u 1s and n minus u zeros. What is the probability of that outcome? Yeah?
And choose
No. I mean, a probability is going to be a number between 0 and 1. In fact, let's say I have a specific outcome. Let's consider the outcome where the first u flips were 1 and the remaining n minus u flips were 0. What's the probability of seeing u 1s and then n minus u zeros? Yeah? Yeah, that's right. It's p to the u times 1 minus p to the n minus u. Another way to think about it is like if you think about the probability tree, right? I mean, you have like n of these Bernoulli p's. So it's like a tree of depth n. And it has like two-way branching for each of them. And whenever you get a 1, the probability for that branch is p. And whenever you have a 0, the probability for that branch is 1 minus p. And I'm interested in all those leaves where you had u many 1s and n minus u many 0s. So remember, the probability of a leaf, an outcome, is like the probability of the product of the probabilities along that path. So it's like you got u times you did p, and n minus u times you did 1 minus p. Okay, and how many outcomes are there where there are u1s and n minus u 0s? It's like how many binary strings are there with u1s and n minus u 0s?
And choose u.
N choose u, yes, exactly. Yeah, n choose u. So, if you must know, this is getting a little bit grungy, but the probability that a binomial random variable equals a specific number u has this mildly intimidating formula. N choose u times p to the u times 1 minus p to the n minus u. Okay, so now we kind of know everything in principle there is to know about this random variable. I mean, I could just write down in a table like it's a random variable, these are the possible values it could take, and here's the formula for the probability it takes each of these values. We could check, these are supposed to be a bunch of numbers that add up to 1. We could endeavor to check this. If you don't follow this part, it's okay, but I put it up because it actually illustrates why it's called a binomial random variable. If you remember algebra, arithmetic, if you ever have like a plus b to the power of n, like you can expand it with this like binomial formula where you get sum over numbers from 0 to n of this thing to the u plus this thing to the n minus u times the binomial coefficient. So this is by the binomial theorem. And then, but see, p plus 1 minus p is 1. So this is just 1 to the n. So it checks out that these numbers add up to 1. I mean, they also have to add up to 1 because, I mean, we just did the calculation, right? This is the true probability that you get u heads if you flip n p-biased coins. But here's another check that illustrates the name. What is the expectation of x? What is the average or expected number of heads you'll get in a second? Well, it's in principle this, right? I mean, you sum over all u's, the probability that x equals u times u. This formula looks even worse than this formula. But it's not too hard to compute. Actually, I mean, what do you think it should be? Yes? Yeah, you should think it should be, n times p, right? I mean, if I flip n coins, each one has a 30% chance of coming up heads. I kind of expect 30% times n heads. And that's correct. And you can get it easily by linearity of expectation, right? X is actually the sum of these xi's that are Bernoulli p. And the expectation of a Bernoulli p random variable, really a Bernoulli p is like an indicator that the ith coin came up heads, which has probability p. So it's n times p. Okay. One more thing, your other favorite random variable is called a geometric random variable. It also has nothing to do with geometry, but I'll attempt to illustrate the reason for the name. This is also another nice random variable that comes up. You can think of it in terms of coin flipping. Here the game is, again, you have a p-biased coin that comes up heads with some probability p. And you just keep flipping it until you get a heads, and then you stop. And then you ask yourselves, how many times did I flip it? Okay? And so we write geometric p for a random variable that's like counting the number of flips it takes to get a head when heads has probability p. Okay, so here would be the code. X starts out at 1. You're always going to flip it at least one time. And then you keep doing Bernoulli p until you get a 0. And as long as you don't, you increment x. So it's good to draw the probability tree here, although something somewhat unusual happens when you do this, which is that it's infinite. But anyway, the first thing you do is a Bernoulli p, and if that's a 1, then you say, I stop, and I did one flip. Otherwise, if it's 0, you do another Bernoulli p. If it's 1, then you stop and say x is 2. I did 2 flips. Otherwise, if it's 0, you do another coin flip. Maybe it's 1 and x equals 3, and you stop. And you keep going until you eventually get a heads. And let's check out all these probabilities. Here it's a little bit easier to compute. What is the probability that x is 1? Well, again, it's just the product of these path probabilities. So this was p. And then this one here is 1 minus p times p. And this one down here is like 1 minus p, 1 minus p, p. Okay, so in general, the range of x, which is geometric random variable, is actually any positive integer. It could be 1, 2, 3, 4, any number of positive integer. And this is a little bit weird. We have not yet actually talked about having a random variable that can take on infinitely many different values. It's okay though. Just don't worry about it. It's basically there's nothing can really go wrong. There's like some mild complications that we're never going to get into. So if you really care about certain issues that I'm glossing over, then you can ask. But it's basically nothing tricky will really happen. Okay, and what is the probability that x is a specific number u? What's the chance that it takes you exactly u flips to get a heads? Well, we saw this before, right? The first u minus 1 flips all have to be tails. That's 1 minus p to the u minus 1. And then the u flip has to be heads. That's p. And we may check that these numbers actually add up to 1. And again, that's actually going to be the reason for why it's called geometric random variable. So we sum over all the outcomes, of which now it's every positive integer is a potential outcome of this formula. And you can factor out the p. And then this thing is a geometric series, hence the name. You know, it's like the sum of like a succession of numbers, each one having the same ratio from the previous one, which is 1 minus p. There's a formula for that infinite sum. It's like 1 over 1 minus the common ratio. So you get p over p, which is 1. Okay, any question about that? Okay, well, once you have like a random variable, the first question should always be, what's its expectation? So let's imagine this. You're flipping a coin, which comes up heads with probability 1 over 5. What is the expected number of flips you need in order to get a heads? What would you guess it is? 5, yeah. Now usually your naive guesses don't turn out to be right. But sometimes life is good, and it's actually right in this case. So everything is happy in this situation. The expected value of a geometric random variable with probability p of coming up heads is indeed 1 over p. And I guess you'll do the proof in recitation tomorrow. Okay, any questions about geometric random variables or binomial random variables or anything else? Okay. So now finally I'm going to tell you about some problems in computer science. First one is a very famous problem in probability called the coupon collector. And it's always sort of like this. Suppose there are n different kinds of coupons. I guess like this was like invented in like the first half of the 20th century, where like you'd buy like maybe breakfast cereal boxes, and each one would have like a coupon like hidden inside, and there'd be many different types, and like you're trying to collect them all. So for some reason, I've actually never played Pokemon before. Like, I know nothing about it, but like when you're trying to collect things, it seems natural. So the scenario is this: there's n different kinds of things, and then at each day you get a random one of them. I mean, there's infinitely many copies of each one. You just wake up, and then somebody gives you one of the n things. All right, you like buy that breakfast cereal, you open it up, and you're like, okay, I got the Charmander coupon. And you may even get duplicates and so forth. So At the beginning, like things are good. You're probably getting like lots of different whatevers. But it's like very hard to get the last few ones because you usually get like a duplicate of something you already have. And the question is, you want to get all of them, get them all. So let x be the number of days until you have all n coupons. And what is the expected value of x? Okay, it's certainly going to take you at least n days. That's the bare minimum, right? And that's probably not going to happen. That would be like a miracle if like you got, well, it could happen, but all unique coupons in your first n tries. And you hope it doesn't take you too long, right? At the beginning, you're going to probably do well. And towards the end, it's going to be slower. So this problem actually comes up a lot in computer science. I think you'll see an illustration of it in the next lecture. I'm not sure. But let's solve this question. And as always, or not as always, but as is very often the case, it's solved by this linearity of expectation plus indicators method. So you have to think of a clever way to write x as the sum of, let's say, n random variables that are easier to analyze. Can anybody think of a suggestion? This is a bit tricky, but OK.
You can develop a week with each coupon.
Ooh, go ahead.
And you're just performing a random walk.
Whoa. A random walk in a clique. It is true, but I mean, it's not really what I was asking. I mean, I was asking, can you think of a way to write this x as a sum of some indicator random variables or some, sorry, not indicators, the sum of some other random variables? Yeah?
You get a new coupon on the ith day.
Yeah, there's two ways to do it. I mean, you want to look at, maybe there's only one way to do it. Yeah, you want to look at the number of days it takes you to go from I minus 1 coupons to I coupons. Like, at the beginning, when you're sitting on 0 coupons, it only takes you 1 day to get the next coupon. And then when you're sitting on 1 coupon, you got to wait. I'm saying, how many days does it take until you get the second coupon? It's probably also going to be 1, unless something very unlikely happens. But this is what I wanted to find. The number of days it takes you in this experiment to get from I minus 1 coupons to I coupons. And then x, the total number of days, is this sum. It's the number of days to get the first unique coupon until the number of days until you have 2 different ones, until the number of days until you have 3 different ones, plus the number of days it took you to get that last, like the last one you needed, the nth unique coupon. Okay, and so then by linearity of expectation, the expectation of x is the sum of these expectations. So we simplified the problem into like trying to compute what each of these separate expectations are. Does that make sense so far? OK. So let's say you're sitting on I minus 1 distinct coupons, and then each day you get like a new one. What's the probability you'll get a new coupon that you don't already have? Yeah, that's right. And so you have I minus 1 in your hand. There's n in total. This is the number of ones on the top that you don't have. And each day you get a totally random one among the n possible coupons. So these are the ones you need. These are the total possibilities. So it's this. OK, so what kind of random variable is xi, therefore? Yeah, it's geometric. Because when you're sitting on I minus 1 distinct coupons, like you're basically, every day it's like a coin flip. Like if it comes up with this probability, it's like you got that ith coupon that you wanted. Otherwise, you didn't. So this is a geometric with this parameter is exactly computing the number of days you waited to get this ith new coupon. And now we're happy because the expected value of this random variable is 1 over this number. Right? The expectation of a geometric p random variable is 1 over p. So it's n over n minus I minus 1. For example, the expected value of x1 is 1. That makes sense, right? How many days does it take you on average to get that first new Pokemon? 1. You always get a new one to you at the beginning. The expected value of x2 is like a number that's just a little bit bigger than 1. Because on the second day, you usually get a distinct one from the first one you got. And you can even also see that the expected value of xn is n, because it's like now you have almost all of them. There's only one you need. Each day you get like a random one. So it's, well, it's geometric 1 over n. It takes you on average n days to get that last one. OK, so now it's arithmetic. The expected value of x is n over n plus n over n minus 1 plus dot 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 plus n over 1. Factor out the n on top and reverse the sum. So it's n times this sum. This is something we saw before. This is like a well-known sum. It doesn't have a closed form, but it almost does. This sum here is called the nth harmonic number. It's just defined to be this. And if you remember back to lecture 8, Professor Ada showed you that it's very close to ln of n, natural logarithm of n. So, I mean, the expectation of x is more or less n times ln n. That's interesting. I mean, the minimum it could have taken you is n days. Maybe it might take you n squared days on average, you might think, or n cubed or something. It's more than n, but not too much more. It's n times natural log of n is the expected number of days. OK. Let me tell you about one more problem. I'm going to analyze with our random variables. And it's my favorite problem. I always bring it up. I can't stop talking about it. Max cut. Let me remind you. I think it's the third time. But you're given a graph. And you're trying to color the vertices of the graph, let's say with 2 colors. And you say an edge is cut if its endpoints have different colors. It's like you're trying to split the people into 2 teams. And you don't want friends to be on the same team. Okay, so you get like a point whenever you split up a pair of friends. So here's an example of a coloring with 2 colors. And here you actually cut almost all the edges. This is the only edge that has an edge with both endpoints on the same team. So what do we know about this problem? One thing we know is that finding the maximum cut is NP hard. That's a fact. On the other hand, the first time we saw this, we gave like a kind of simple polynomial time algorithm based on like, it was called local search, that was guaranteed to find a 2 coloring in the end that at least cut half of the edges. And we were like, well, that's not bad. I forget what the running time was, maybe order m times n or something. Today, what I want to tell you is like another super duper simple algorithm that in fact runs in order n time. In fact, it's very, very simple. It has basically the same guarantee. And it's so simple that it actually doesn't even really look at the graph. It's like you give it the graph and it's like, you know, that's all right. Don't even bother telling me. Here's my 2 coloring. And it more or less is going to have this guarantee. So how does it do that? Just outputs a random 2 coloring. Okay, just splits the vertices into 2 groups, group 1 and group 2 randomly. So this is the whole pseudocode. That's it. Okay, you go through all the vertices and set the vertex's color to like, let's call the colors 1 and 2, just random 2. That's it. Very fast. Now let's see what its like solution quality is. Let's say an expectation. So let's let x be the random variable giving the number of edges cut. And let's figure out what the expected value of x is. So it's not like, this algorithm's not going to actually guarantee that it cuts a lot of edges, but it's going to, the expected value is going to be pretty big. And that's more or less OK. Like if you, sort of on average when you run it, you'll cut at least this many edges. And so you can run it a few times and pick the best one that you got. OK, well, our favorite method is going to help us out here. So let x be the number of edges cut. And we're going to, again, want to represent x as the sum of some indicator random variables. And we're going to have one indicator random variable for each edge, naturally. So for each of the edges e, let b sub e be the event that it gets cut by this little algorithm. And let x sub e be the indicator random variable for this. So x sub e is just 1 or 0, depending on whether this particular edge e got different color endpoints. And x, the total number of edges cut, can be written as the sum over all edges of x sub b. Just like you go through all the edges, count 1 whenever it got cut. X is the total number of cut edges. Okay. So by linearity of expectation, the expected value of the number of cut edges is the sum of the expected value of the xe's. And there are other basic factors that if you have an indicator random variable, its expectation is the probability of the event that it's indicating. That's the sum over all edges of the probability that that edge gets cut, that that friendship gets broken up by this random coloring. So we just need to figure out what that is. So if you have this edge and you color all the vertices randomly, what's the probability that it gets cut? Yeah, it's a half because, well, I mean, it gets cut if this one is 1 and this one is 2, or vice versa. And there's 4 possibilities: 1, 1, 1, 2, 2, 1, 2, 2. Okay, so every single one of these probabilities is a half. And so the expectation of x is a half times n, which is not bad. I mean, this is basically the same guarantee. So actually, on one hand, the local search algorithm had some better properties in the sense that it always for sure found, it was deterministic, and it always for sure found a 2 coloring that cut at least half of the edges. This one, it's only probabilistic. Sometimes it'll give you more than half the edges. Sometimes it'll give you less than half the edges. But on average, it gives you half the edges. And as I said, it's not too hard to show also that if you just run it a bunch of times, you know, you're probably going to get some that are more than half the edges. And you can just take the best coloring you got. And it's also much faster and simpler. I mean, the other one is a bit complicated. You need some data structure. It was merely polynomial time. This one is just like 2 lines of code. And it really illustrates like the miracle of this method. I mean, you don't need to know anything about the graph. Like it always works. Okay, let me close with one more similar, but somehow even more interesting example. This is about a problem called max 3-sat. It's similar to 3-sat, but it's like a optimization version. So let's let S be like a 3-sat formula. Okay, it's like a CNF where each clause has exactly 3 literals. Okay, so something like this. Now, we know that 3-sat is NP hard. Like, if I give you a satisfiable formula, it's NP hard to find a satisfying assignment. But in this approximation algorithms, lecture, we said, don't give up. Like, just try to do the best thing you can. And this max 3-sat question is really about that. So try to find a truth assignment that makes as many of these size 3 clauses as true as you can. Just, maybe it's going to be hard for you to make all of them true, but just do your best. Try to get a lot of them to be true. Okay, now this is also a pretty hard problem. I mean, you can think of some different heuristics you may try, and they don't really work so well. Here's like the dumbest thing you could try. Just try a random truth assignment. I mean, it's at least going to be a fast algorithm. I mean, really, you just go through each variable, set it to be true or false randomly, and like cross your fingers. Same with the max cut. So let's analyze again how well this does. Let x be the random variable which counts the number of clauses that you satisfy. What is this in expectation? Well, just as with the max cut, it's very similar. We can write it as the, by linearity of expectation, the sum of the expectations of xj, where xj is the indicator that the jth clause got satisfied. And that's the probability that the jth clause got satisfied. And come somebody tell me if you have like a fixed clause, like, I don't know, the first clause here, you set all the variables' truth values at random, what's the chance that this thing will be satisfied? Not quite. Something like that, though. Yeah? Yeah, 7/8. Yeah, because there's 8 possibilities, right, for the 3 truth assignments here. And it's an or, so like exactly one of them is unsatisfying when you like set x1 to be false, x2 to be false, and x3 to be true here. And it's going to be the same for each clause. 1 out of the 8 possibilities is unsatisfying. 7 out of the 8s are satisfying. So each clause individually is satisfied with probability 7/8. And so you sum, all these numbers are 7/8, and you satisfy 7/8, which is 87.5% of the clauses in expectation. which is good, although your dream is to try to satisfy all of them, or maybe 99% would be better, or 90%. So we know given a satisfying assignment, even if there is one that's an assignment that satisfies all of them, it's NP hard to find it. There's this super duper simple algorithm that will at least get 87.5% in expectation. And as always, we should ask, can we do better? And the answer is actually more or less no. Which is kind of amazing. So this is a theorem proven in 97 by this famous guy, Hostad. Given a satisfiable 3CNF formula, it's actually, even if I give you a 3CNF formula and I tell you, I swear to God, it's satisfiable, it's NP hard to find a truth assignment satisfying anything more than 7/8 of the clauses. Not only is it hard to find the satisfying assignment, it's hard to even beat this randomized algorithm. So in some ways, this randomized algorithm is the best polynomial time algorithm for max 3-sat. That's kind of crazy. I guess it just really illustrates how hard this 3-sat problem really is. Okay, new homework will be out. See you on Tuesday.